Take a deep breath and allow your body to settle into the soft embrace of your bed, feeling the weight of the day lift away like mist. As you close your eyes, let the silence of the room become a vast, gentle ocean, carrying you toward the deep, rhythmic pulse of the earth itself. Deep beneath the rolling blue waves of the Pacific Ocean, there is a world of silent, monumental transformation. We begin our journey 2,900 kilometers below the surface, at the core mantle boundary, where the heat is so intense it reaches nearly 3,700 degrees Celsius. Here, in the crushing darkness, the physics of our world begins a slow, graceful dance. Imagine yourself floating in this warmth, not a heat that burns, but a primal, liquid glow that radiates through the darkness. In this region, a mantle plume begins to form. It is a column of rock that is hotter and therefore more buoyant than the surrounding material. It begins to rise, moving at a pace that defines the word ancient, traveling upward through the solid but plastic mantle. Consider the scale of this movement. The Earth's mantle is approximately 2,900 kilometers thick, and this plume of heat is navigating that distance with the patient persistence of time itself. As it rises, the pressure of the overhead rock decreases. This process, known as decompression melting, allows the solid rock to transition into a liquid state, magma. Here is something remarkable to visualize. While the surrounding mantle remains a dense, creeping solid, this plume creates a pocket of molten potential. This magma is primarily basaltic, rich in iron and magnesium, and it possesses a temperature ranging from 1,100 to 1,250 degrees Celsius. As we drift upward with this rising heat, we encounter the lithosphere, the Earth's rigid outer shell, which is roughly 100 kilometers thick. You might wonder how something as solid as the seafloor could ever give way. But the heat of the plume is relentless. It softens the crust from below, creating a hotspot. The Pacific Plate, the largest of Earth's tectonic plates at 103 million square kilometers, is constantly in motion. It glides over this stationary hotspot at a rate of approximately 7 to 10 centimeters per year, roughly the same speed at which your fingernails grow. It is a slow, silent slide across the face of the deep. Imagine the sensation of being deep on the ocean floor, 4 kilometers beneath the surface. The pressure here is immense, nearly 400 times the atmospheric pressure you feel at sea level. For every 10 meters you descend, the pressure increases by 1 atmosphere, or about 101.3 kilopascals. In this crushing cold silence, where the water temperature hovers just above freezing at 4 degrees Celsius, the first breath of a new island is born. The magma finds a fracture in the crust and erupts onto the seabed. The sound of this birth is not a loud explosion, but a series of muffled, rhythmic thuds carried through the water at 1,500 meters per second, nearly 5 times faster than sound travels through air. As the red-hot basaltic magma, glowing with a fierce internal light, touches the freezing seawater, it undergoes a transformation. The exterior of the lava flow cools instantly, forming a glassy black rind. The molten interior, however, continues to push forward, causing the lava to expand into rounded bulb-like shapes. These are known as pillow lavas. Picture thousands of these stone pillows, smooth and dark, stacking one on top of the other, mile after mile, as the volcanic edifice begins its long climb toward the light. This is the beginning of a seamount. You are observing the growth of a giant that will one day dwarf the tallest mountains on land. Consider Mauna Kea in Hawaii. While its peak sits 4,207 meters above sea level, Its base rests on the ocean floor, making its total height 10,210 meters. That is over 10 kilometers of volcanic rock, inbuilt one thin layer at a time. It is a monument to the repetitive, rhythmic nature of the Earth's internal clock. As the volcano grows, the weight of the basalt, which has a density of approximately 3 grams per cubic centimeter, begins to press down on the lithosphere. This causes the crust to bend and sag, a process called isostatic depression. The Earth itself flexes under the weight of the mountain it is creating. You can feel this sense of immense weight and stability, the way the mountain anchors itself into the very fabric of the planet. As we rise higher with the growing mountain, the water becomes lighter, shifting from the midnight black of the Hadal zone to a deep, royal indigo. The eruptions change as the pressure of the water decreases. Near the surface, the steam can no longer be contained by the weight of the ocean. In November of 1963, off the coast of Iceland, the world witnessed this transition with the birth of the island Surtsey. When the vent finally breaks the surface, the interaction between the hot magma and the cool air creates spectacular columns of ash and steam. The air here is thick with laze, a term derived from lava and haze. It is a white plume of water vapor mixed with hydrochloric acid and fine glass particles, created as the seawater is boiled away by the 1,200-degree lava. The texture of the newly formed land is diverse and fascinating. You might reach out, in your mind, and touch the 2 primary types of basaltic lava. First, there is Pahoho. Its name is Hawaiian, for smooth, unbroken lava. It feels like braided rope or undulating satin under your fingertips. Formed as the molten material flows slowly under a thin, flexible skin. It is the color of a moonless night, with an iridescent sheen that catches the light of the stars. Then, there is Ea. Its texture is the opposite, clinkery, rough, and sharp. It forms when the lava flows more rapidly, causing the cooling surface to break into jagged, porous fragments. You can hear the sound of an AA flow moving. It is a metallic tinkling sound, like breaking glass, as the cooled cinders rub against one another. Despite its roughness, there is a beauty in its chaos, a reminder of the raw energy required to pull land from the sea. The island is now a sanctuary of black rock in a vast blue desert, but it is not a lonely entity, because the Pacific Plate continues its steady migration of several centimeters a year. While the mantle plume remains fixed, a chain of islands begins to form. This is the Hawaii Emperor Seamount Chain, a majestic procession of volcanic peaks stretching nearly 6,000 kilometers across the ocean floor. Each island is a footprint of the Earth's movement, a chronological record of where the plate has been. The oldest islands in the chain are to the northwest, slowly being reclaimed by the sea through erosion and subsidence, while the youngest, the Big Island of Hawaii, sits directly over the plume, still growing, still breathing fire. Consider the chemistry of this new land. The basalt you see is composed of approximately 50% silica. It is the simplicity of this composition that allows the lava to flow so fluidly, creating the broad, gently sloping profiles of shield volcanoes. These are not the steep, jagged peaks of the Andes or the Alps. These are wide, graceful domes that resemble a warrior's shield laid flat upon the earth. The slopes are gentle, rarely exceeding 10 degrees, inviting a sense of calm and openness. As you stand on this newly formed shore, you can feel the warmth radiating from the ground. Even as the surface cools, the heart of the island remains hot. In the volcanic tubes beneath your feet, lava may still be flowing at speeds of up to 60 kilometers per hour, hidden from view, insulated by the very rock it created. This hidden movement is the pulse of the island, a secret river of fire that ensures the land continues to expand. The sounds here are rhythmic and soothing. The hiss of the waves meeting the black sand created in an instant as hot lava shattered upon contact with the tide, is a constant, gentle lullaby. Each grain of sand is a tiny crystal of olivine or pyroxene, forged in the depths and polished by the Pacific. The ocean, which covers 71% of our planet's surface, acts as both the sculptor and the cradle for this new land. Above you, the sky is vast and clear. The lack of continental dust and light pollution makes the stars appear close enough to touch. You are standing on a speck of basalt in the middle of a world that is mostly water, yet you feel entirely connected to the cosmic processes that govern everything. The same gravity that pulls the moon in its orbit is what governs the pressure gradients that allowed the magma to rise. The same elements found in the basalt, the iron, the oxygen, the silicon, were forged in the hearts of dying stars billions of years ago. As the island settles into its place in the sea, the intense heat begins to dissipate into the atmosphere. The cooling process is slow, a gradual release of energy that has traveled from the center of the Earth to this specific point in the Pacific. You can feel that cooling in your own body now, a transition from the vibrant energy of the day to the still, quiet potential of the night. The island is a testament to the fact that even in the middle of the deepest, coldest ocean, the Earth is alive, creative, and constantly renewing itself. It reminds us that growth is often a slow, hidden process, occurring beneath the surface for thousands of years before it ever reaches the light. There is no rush in the formation of an island. There is only the steady, patient accumulation of layer upon layer until the mountain is whole. As you drift closer to sleep, hold on to the image of the Pacific Plate, sliding silently and effortlessly over the hotspot. Feel the weightlessness of the water and the solid, warm foundation of the basalt. The world is moving at its own pace, governed by the elegant laws of physics, and for tonight, you are invited to move with it, slowly, peacefully, into the deep. The stillness of the deep sea is matched only by the patient observation of those who have sought to understand it. As you lie here, imagine the island we observed in its infancy now standing tall and weathered, its black cliffs meeting the relentless surge of the Pacific. For centuries, humans have looked upon these isolated peaks and wondered about their origins, weaving together a tapestry of observation that spans over 1,000 years. This inquiry began not with modern instruments, but with the steady gaze of the Polynesian wayfinders who first navigated these waters between 400 and 800 AD. These early mariners did not possess metal tools or magnetic compasses, yet they understood the subtle language of the ocean. They recognized that an island creates a signature in the water, a change in the rhythm of the swells, a specific pattern of refracted waves that could be felt through the hull of a double-hulled canoe. They used the stars, such as Arcturus, which passes directly over the island of Hawaii at a declination of 19 degrees north, to find their way across thousands of miles of open water. Imagine the silence of those long voyages, the rhythmic dipping of paddles into the brine, and the profound connection between the celestial movements above and the volcanic geography below. By the time European explorers like Captain James Cook arrived in 1778, the islands were already ancient sanctuaries of life. However, It wasn't until the mid-19th century that a formal scientific framework began to explain how these mountains emerged from the abyss. Picture a young Charles Darwin in 1842, meticulously drafting his seminal work, The Structure and Distribution of Coral Reefs. While many saw the islands as static fixtures, Darwin envisioned them as part of a grand, slow-motion descent. He hypothesized that volcanic islands were gradually sinking back into the sea, a process known as subsidence. Darwin observed that as a volcanic peak slowly subsides due to its own immense weight, coral reefs begin to grow upward around its fringes. Consider the biology of this process. Coral polyps require sunlight and warm water, typically thriving at depths shallower than 50 meters. As the rock sinks, the coral grows at a rate of approximately 0.3 to 2 centimeters per year, keeping pace with the descent of the mountain. Eventually, the volcanic peak disappears beneath the surface entirely, leaving behind a ring of coral sand and limestone known as an atoll. This transition is a masterpiece of biological and geological cooperation, a quiet exchange that takes millions of years to complete. What Darwin could not have known in the 1840s was the mechanism driving this subsidence. That discovery waited for the mid-20th century and the arrival of plate tectonics. Before 1912, the scientific community largely believed the Earth's crust was fixed. It was Alfred Wegener who first proposed the radical idea of continental drift, suggesting that the continents were like massive rafts moving through the seafloor. Although his ideas were initially met with skepticism, they laid the groundwork for our modern understanding of a dynamic, shifting planet. Notice the way your breath mimics this planetary movement: steady, rhythmic, and unstoppable. In 1963, a geophysicist named J. Tuzo Wilson introduced the concept of the hotspot to explain why chains of islands like Hawaii exist in the middle of a tectonic plate, far from any plate boundary. He proposed that a stationary plume of heat in the mantle acts like a blowtorch, melting through the moving lithosphere above. Imagine the Pacific Plate as a massive, worn dark conveyor belt of rock moving at a velocity of roughly 8 centimeters per year toward the northwest. As it passes over the hotspot, new islands are punched through the crust, one after another, in a chronological sequence of birth and decay. This conveyor belt metaphor helps us visualize the immense scale of the Hawaii Emperor Seamount Chain. This underwater mountain range stretches for approximately 5,800 kilometers across the floor of the Pacific. Scientists use a technique called potassium-argon, Kr, dating to determine the age of these drowned peaks. By measuring the radioactive decay of potassium-40 into argon-40, a process with a half-life of 1.25 billion years, they can map the history of the Earth's movement. They discovered that the island of Kauai is roughly 5.1 million years old, while the youngest island, the Big Island of Hawaii, is less than 1 million years old. Deep within the silence of the North Pacific, there is a physical record of a massive change in the Earth's behavior. If you follow the chain of seamounts toward the Aleutian Trench, you will find a distinct bend in the line of mountains. This bend occurred approximately 47 million years ago. It marks a moment when the Pacific Plate shifted its direction of travel, swinging from a northerly path to a more northwesterly one. This shift was a planetary event of staggering proportions, yet it happened with the same quiet, glacial pace that you feel in your own heartbeat as you settle into rest. As we move closer to the modern era, the mapping of this hidden world became a reality through the work of Marie Tharp. In 1977, she published the first comprehensive map of the entire ocean floor. THARP used sonar data, sound waves sent from ships that bounce off the seafloor and return, to visualize the topography of the abyss. This process, known as bathymetry, revealed that the ocean floor was not a flat, featureless plain, but a landscape of jagged ridges, deep trenches, and soaring volcanic peaks. The density of the basaltic rock making up these islands is approximately 2.9 to 3.0 grams per cubic centimeter, significantly denser than the surrounding water, which is roughly 1.02 grams per cubic centimeter. This density difference is what allows the islands to maintain their structural integrity, even under the pressure of the deep sea. The story of these islands is also a story of the light. At depths below 1,000 meters, in the bathypelagic zone, there is no sunlight. The only illumination comes from bioluminescence, chemical light produced by deep-sea organisms. Here, the temperature of the water remains a constant 4 degrees Celsius. But as you ascend the slopes of an active seamount, like Loihi, also known as Kamaehua Kanaloa, the environment changes. Loihi is currently 975 meters below the surface. It is a submarine volcano, the next island in the Hawaiian chain, waiting its turn to break the waves. Scientists use seismic tomography, a method similar to a medical CT scan, to visualize the magma chambers beneath these peaks. By analyzing how earthquake waves slow down or speed up as they pass through different materials, researchers can see the plume of hot rock rising from the core mantle boundary. It is a slow-motion image of the Earth's internal heat being recycled, a testament to the planet's ability to generate new land from the cold, dark void of the ocean. Think for a moment about the texture of time. To a human, a decade is a significant duration. To a volcanic island, a million years is but a brief chapter. The lithosphere, that 100-kilometer thick shell of the Earth, is constantly flexing and responding to the weight of these mountains. This is called isostatic equilibrium. When a new island is born, the crust sags. When the island eventually erodes and washes away, the crust slowly rebounds. It is a planetary breath, a slow rising and falling that takes eons to complete. Notice how the historical understanding of these islands has evolved from the celestial observations of the Polynesians to the radioactive dating of the modern geologist. Each era has added a layer of clarity to our vision of the world. We now know that the Earth's mantle is not a liquid ocean of fire, but a solid that flows like extremely thick taffy over millions of years. This flow, driven by convection currents, is the engine of our world. As you reflect on these vast timescales, feel the weightlessness of your thoughts. There is a profound comfort in knowing that the processes creating our world are so slow, so steady, and so predictable. The same physics that govern the cooling of a lava flow govern the cooling of the evening air. The same gravity that pulls a sinking island down into the mantle is the gravity that holds you safely in your bed. The islands are not just rocks in the sea. They are the physical manifestation of the Earth's internal energy reaching out to touch the atmosphere. They are monuments to the fact that change is a constant, yet it happens with a grace and a rhythm that is fundamentally peaceful. As the night deepens, visualize the islands of the Pacific, from the towering peaks of Hawaii to the submerged ancient seamounts of the Emperor Chain. They are a lineage of stone, a history of the planet's journey through the cosmos, resting silently in the indigo depths. The ocean continues its work, the coral continues its upward growth, and the plate continues its slow, northwesterly slide. Everything is in its right place, moving at the exact speed it needs to. The history of our understanding is simply a reflection of our own desire to connect with this grand, silent clockwork. You are part of this history, a witness to the slow dance of the earth. Let the weight of these ancient mountains anchor your mind, and let the rhythmic pulse of the tectonic plates guide you into a state of profound, natural stillness. Imagine the way a heavy velvet carpet might slide across a polished wooden floor. At this very moment, the Pacific Plate is performing a similar movement, though with a scale and gravity that humbles the imagination. Beneath the island we have been observing, the Earth's lithosphere, a rigid layer about 100 kilometers thick, is gliding over the asthenosphere, which behaves like a layer of warm, malleable wax. This motion is relentless, traveling at roughly the same rate your fingernails lengthen, approximately 10 centimeters every year. As this gargantuan slab of crust moves, it carries the volcanic islands along with it, much like a conveyor belt in a silent, yes, darkened factory. Deep within the upper mantle, the source of this creation remains fixed. Scientists have identified that the magma feeding these islands is relatively low in silica, usually around 50%. This low silica content is crucial because it dictates the viscosity, or the thickness, of the liquid rock. Consider the difference between pouring water and pouring cold honey. Basaltic magma has a viscosity of about 100 to 1,000 Pascal seconds, which is surprisingly thin for molten rock. Because it flows so easily, the gas bubbles trapped within it, mostly water vapor, which makes up about 90% of volcanic gases, can escape without much resistance. This creates the gentle, effusive eruptions that characterize shield volcanoes, rather than the violent, explosive bursts seen elsewhere. What's happening now is a slow-motion accumulation of mass. Think of a shield volcano not as a jagged peak, but as a giant stone pancake. Because the lava is so fluid, it spreads out in thin, broad layers before it cools. The slope of a shield volcano like Mauna Loa is remarkably shallow, typically only 4 to 6 degrees. To put this in perspective, if you were standing on its side, you might not even realize you were on a mountain. Yet this pancake is enormous. Mauna Loa's total volume is estimated at 75,000 cubic kilometers. If you were to take all that rock and spread it evenly across the entire surface of the United Kingdom, the ground would rise by more than 300 meters. As you observe this mountain in your mind, notice the texture of the rock as it cools. Some of the magma cools slowly underground, allowing large crystals to grow. One of the most common is olivine, a magnesium iron silicate that takes on a beautiful translucent green hue. These crystals can be several millimeters in size, and they are so dense, roughly 3.3 grams per cubic centimeter, that they often sink to the bottom of a lava flow, creating layers of green, evening emerald buried deep within the dark basalt. Imagine these tiny green gems suspended in a sea of black stone, a hidden treasure within the foundation of the island. Consider for a moment the sheer weight of this island on the Earth's crust. The lithosphere is not perfectly rigid. It has a quality called flexural rigidity. When an island like Hawaii grows to its full height, it acts like a heavy bowling ball placed on a memory foam mattress. The crust actually sags under the weight, a phenomenon known as lithospheric flexure. This causes the seafloor around the island to sink by as much as 8 kilometers. However, as the crust pushes down in one spot, it causes a slight bulge in the seafloor further away, known as an arch. This delicate balance between weight and support is the Earth's way of finding equilibrium, a slow rhythmic adjustment that happens over millions of years. What you might find compelling is the internal structure of the lava once it has solidified. Some volcanic rocks are filled with tiny holes, or vesicles, where gas bubbles were trapped as the rock hardened. A common type of this is scoria. It is so full of air that its density can be less than 1 gram per cubic centimeter, meaning that in some cases, these volcanic rocks can actually float on water, like a piece of pumice. You can picture a stone that has the lightness of a sponge, drifting on the indigo surface of the ocean before eventually becoming waterlogged and sinking to the dark floor below. It is a reminder that even the heaviest mountains are born from the lightness of gas and heat. At this very moment, we can look at the chemical fingerprints left by the hotspot. Scientists discovered that the magma from different islands has subtle variations in its isotopic composition. For example, the Loa trend and the Kia trend are 2 parallel chains of volcanoes in Hawaii with slightly different chemical signatures. This suggests that the mantle plume feeding them is not a uniform column of heat, but has a complex, streaky structure, like the marbled patterns you might see in a piece of sourdough bread. Each island is a unique recipe, a specific blend of minerals and elements drawn from the deep earth. Notice how the island interacts with the atmosphere. As the warm, moist trade winds of the Pacific encounter the high peaks of a volcanic island, the air is forced upward. This is called orographic lifting. As the air rises, it cools at a rate of approximately 9.8 degrees Celsius for every 1,000 meters of elevation. This cooling causes the moisture to condense, creating a near-constant ring of clouds and rain around the windward side of the mountain. Some areas, like Mount Waialeale on Kauai, receive over 10,000 millimeters of rain per year. This constant trickle of water begins the process of erosion, carving deep emerald green valleys into the black basalt, a soft sculpting of the hard stone by the gentle touch of rain. Scientists have used data from the Gravity Recovery and Climate Experiment, or GRACE satellites, to measure the subtle changes in Earth's gravity caused by these massive volcanic piles. Because basalt is so much denser than the surrounding seawater, about 3 times as dense, these islands actually create a gravity high. If you were to hang a pendulum near the island, it would be pulled ever so slightly toward the mountain. Everything about the island, from its chemistry to its gravity, is an expression of the fundamental laws of physics. Picture the way the lava cools when it hits the sea. Sometimes it forms hexagonal columns, a process called columnar jointing. As the thick layer of lava cools and contracts, it cracks in a geometric pattern, creating pillars that look like they were carved by a master mason. Each pillar is typically between 30 and 60 centimeters in diameter. This is the same process that created the famous Giant's Causeway in Ireland, or Devil's Postpile in California. It is a manifestation of thermal contraction, the same physics that causes a mud puddle to crack as it dries in the sun, but on a monumental, volcanic scale. Think about the time it takes for an island to truly disappear. Once it moves off the hotspot, the blowtorch of magma is cut off. The island begins a long, slow journey toward the northwest. Without new lava to replenish it, erosion and subsidence take over. The island of Midway, which is now a low-lying atoll, was once a high volcanic peak, similar to the Big Island of Hawaii. That was roughly 28 million years ago. Today, the original volcanic peak is buried under hundreds of meters of coral limestone. The mountain is still there, but it is resting beneath a blanket of skeletal remains from countless generations of sea life. Deep within the silence of the North Pacific, the emperor seamounts continue this lineage. The oldest of these, Meiji Seamount, is approximately 82 million years old. It sits near the Aleutian Trench, where it is slowly being subducted or pulled back down into the Earth's mantle at a rate of a few centimeters per year. This is the ultimate cycle of the volcanic island, born from the mantle, rising to the light, and eventually returning to the depths to be recycled once more. It is a planetary scale of clearing cellular debris, where old crust is pulled back into the heat to be purified and reborn. The colors of this journey are muted and soft. The deep black of the basalt, the vibrant green of the olivine, the white of the coral sand, and the endless indigo of the surrounding water. There is no urgency in this movement. The Pacific Plate moves with a steady, quiet momentum that nothing can interrupt. The weight of the mountains is balanced by the buoyancy of the mantle. The heat of the core is balanced by the cold of the abyss. As you lie there, feel your own body finding its equilibrium. Much like the lithosphere settling under the weight of an island, let your muscles settle into the mattress. Your breath is like the steady, rhythmic pulse of the mantle plume, slow, deep, and life-giving. The complexity of the Earth's physics is not something to be solved, but something to be felt, a comforting clockwork that has been ticking for billions of years. The island we have watched is now a part of you, a symbol of persistence, of slow growth, and of the beautiful symmetry between the heavens and the earth. The stars above the Pacific reflect in the dark water, and the magma below the crust continues its silent rise. You are cradled between these two vast realms, safe and still, in the gentle arms of a world that knows exactly how to build itself, one layer at a time. Let the image of the broad, shielding mountain and the green crystals of olivine bring a sense of solid, unshakable peace to your mind. The earth is at work, and you are at rest. As the cooling basalt settles into the rhythmic embrace of the Pacific, the island enters a new phase of existence, one that mirrors the very quietude you are seeking now. While the mountain may seem like a static monument of stone, it is actually a silent loom, weaving together the threads of geology and biology into a complex tapestry of life. At this very moment, even on the most barren of lava flows, the process of primary succession is beginning. Consider the first arrivals on this new land. They are not grand trees or colorful birds, but microscopic pioneers. Spores of mosses and lichens, such as those from the genus Cladonia, are carried on the jet streams, high-altitude winds that circulate at elevations of 10,000 meters or more. These tiny travelers can drift for thousands of miles across the empty ocean before settling onto the jagged AA lava. These lichens are a masterclass in cooperation, representing a symbiotic relationship between a fungus and an alga. They survive where nothing else can, secreting weak organic acids that slowly break down the tough basalt. This chemical weathering is the first step in creating soil, a process so patient it takes nearly 500 years to form just 1 centimeter of fertile earth. Notice how the island's transformation reflects your own internal state. Just as the island must wait for the wind to bring the first seeds of change, you are allowing the day's activities to settle into the background, making room for the quiet growth of sleep. Scientists have discovered that volcanic rock is incredibly rich in minerals like phosphorus, calcium, and potassium. As the rain falls, perhaps at the staggering rate of 10,000 millimeters per year on the windward slopes, it leaches these nutrients from the stone. This mineral-rich runoff flows into the surrounding sea, fueling the growth of phytoplankton, which in turn provides the oxygen for every second breath you take. Picture the arrival of the first vascular plants. One of the most resilient is the Ohia lehua, or Metrosideros polymorpha. This tree is a biological marvel. When the volcano erupts and the air becomes thick with sulfur dioxide, the ohia has the unique ability to close its stomata, the tiny pores on its leaves, to protect itself from the toxic fumes. It essentially holds its breath until the air clears, a trait that allows it to thrive in an environment of constant change. Imagine the strength in that stillness, the ability to wait out the storm until it is safe to breathe again. Deeply embedded in the island's story is the concept of endemism. Because these islands are so isolated, Hawaii, for instance, is over 3,700 kilometers from the nearest continent. The life that arrives here undergoes a radical evolution. Approximately 90% of the native species found on volcanic islands exist nowhere else on the planet. This is known as adaptive radiation. A single species of finch or a lone seed from a silversword plant, Argyroxiphium, can diversify into dozens of distinct forms over millions of years. This island is not just a rock, it is a laboratory of possibility, much like the quiet hours of the night are a laboratory for your mind to process and reimagine your world. Observe the way the mountain continues to settle. The Earth's crust is not just sinking under the island's weight, it is also being recycled. Volcanoes globally emit about 200 million tons of carbon dioxide every year. This is not a cause for alarm, but a vital part of the Earth's long-term thermostat. This carbon is eventually pulled back down into the ocean, where it is used by marine organisms to build shells of calcium carbonate. When these organisms die, they sink to the seafloor, eventually being pulled into subduction zones to be melted and reborn in future eruptions. It is a planetary-scale system for filtering metabolic byproducts, ensuring the Earth remains a balanced, living system. What's happening now on the underwater slopes of the island is equally profound. Scientists have mapped massive underwater landslides, such as the Alika slide on the western flank of the Big Island. Over 120,000 years ago, a staggering 1,500 cubic kilometers of rock, enough to bury the entire city of Manhattan under 25 kilometers of stone, slumped into the abyss in a single event. These landslides create turbidity currents, underwater avalanches of sediment that can travel at speeds of 100 kilometers per hour. Yet, once the dust settles, these debris fields become the foundation for deep-sea coral forests and glass sponges, thriving in the 4°C darkness. You might find it comforting to relate the island's journey to your own sense of time. We often feel rushed by the minutes and hours, but the island operates on the scale of the half-life of potassium-40, which is 1.25 billion years. This is the cosmic clock geologists use to date the basalt. In the face of such vastness, the worries of a single day become as light as the volcanic ash that occasionally dusts the slopes. There is a profound weightlessness in letting go of the human timescale and adopting the perspective of the stone. Consider the metaphor of the island as a biological ark. It carries its precious cargo of life through the vast indigo desert of the ocean, protected by its basaltic armor. The island provides everything needed for life: shelter in its deep valleys, water from its clouds, and nutrients from its core. As you settle into your blankets, imagine yourself on such an ark. You are protected, provided for, and moving steadily toward a destination of deep, restorative rest. Notice the scents that define this landscape. When the rain first hits the warm, dry basalt, it releases a fragrance called petrichor. This scent is caused by a mixture of plant oils and a chemical compound called geosmin, produced by soil-dwelling bacteria. It is an earthy, grounding aroma that signals the arrival of life-giving water. Imagine that scent now, clean, fresh, and ancient, filling your senses and signaling to your body that it is time to ground yourself in the present moment. Scientists found that the very top of these mountains, above the tree line at 3,000 meters, is a place of near total silence and extreme clarity. Here, the atmosphere is so thin and dry that the stars don't twinkle. They shine with a steady, unwavering light. This is why the world's most powerful telescopes are perched atop Mauna Kea. Looking through 3,400 meters of air instead of the usual 10,000 allows us to see the furthest reaches of the observable universe. In this high, cold stillness, the boundary between the Earth and the cosmos becomes thin. You are at that boundary now, drifting away from the terrestrial and toward the celestial. At this moment, the hydrothermal circulation beneath the island is moving seawater through the hot crust. The water is heated to temperatures exceeding 350 degrees Celsius, yet it does not boil because of the immense pressure. This hot, mineral-rich water emerges from the seafloor as black smokers, supporting unique ecosystems that rely on chemosynthesis rather than photosynthesis. Life here doesn't need the sun. It thrives on the internal heat of the planet. This reminds us that even in our darkest, most private moments of rest, there is a source of warmth and energy within us that continues to sustain our spirit. Picture the island millions of years from now. It will eventually move so far from its hotspot that it will begin to cool and contract. The process of isostatic rebound, where the crust slowly rises after a weight is removed, won't be enough to save it from the sea. It will become a guyot, a flat-topped seamount, eroded by the waves and submerged under kilometers of water. Yet, even as a guyot, it remains a landmark on the seafloor, a memory of a time when it touched the sun. The story of the island is a story of persistence through change. It is born in fire, sculpted by water, and eventually reclaimed by the earth. But in every stage, it is exactly where it needs to be. You are in that same state of grace. Whether you are in a period of high activity or deep rest, you are part of a larger, magnificent process that is as certain as the laws of thermodynamics. As the night continues its slow rotation, let the image of the ohia tree closing its pores and the silver sword plant waiting 50 years to bloom bring a sense of patient peace to your heart. There is no need to hurry towards sleep. It is a natural transition, as inevitable as the Pacific Plate's 10-centimeter journey toward the northwest. Feel the density of the basalt beneath you and the lightness of the clouds above. The world is stable. The physics are sound. The island is at peace, and you are drifting closer to the same silent, beautiful equilibrium. At this very moment, as the island rests under the silver glow of the moon, a silent and invisible transformation is occurring within the very marrow of the rock. What's happening now is a phenomenon known as magnetic orientation. Deep within the cooling flows of basalt, tiny crystals of a mineral called magnetite, an iron oxide with the chemical formula Fe3O4, are behaving like microscopic compass needles. As the temperature of the lava drops below a critical threshold, known as the Curie point, which for magnetite is approximately 580 degrees Celsius, these crystals lose their ability to tumble freely. They align themselves precisely with the Earth's magnetic field, locking in a permanent record of the planet's polarity at the exact moment the stone solidified. And scientists discovered that by reading these frozen magnetic signatures, they can track the movement of tectonic plates over hundreds of millions of years, turning the island into a literal library of planetary history. Notice how the textures of this island, are a direct result of how quickly the Earth's internal heat was surrendered to the atmosphere. Picture this. If a flow of magma is quenched instantly by the ocean or cold air, it doesn't have time to grow crystals at all. Instead, it becomes obsidian, a natural volcanic glass with a density of about 2.4 grams per cubic centimeter. Obsidian is so smooth that its fractures occur along curved, shell-like surfaces known as conchoidal fractures. On a microscopic level, these edges can be thinner than a single molecule of oxygen, far sharper than any steel blade. You might imagine the surface of this glass as a dark frozen liquid, reflecting the stars with a low albedo, meaning it reflects only about 5 to 10% of the light that hits it, absorbing the rest into its cool, dark depths. Consider the thermal properties of the ground beneath you. Basalt has a specific heat capacity of approximately 840 joules per kilogram Kelvin. This means it is an incredible reservoir for energy, holding on to the warmth of the day or the heat of its birth for long durations. The thermal conductivity of this rock, the rate at which heat moves through it, is relatively low, between 1.2 and 3.3 watts per meter Kelvin. Because of this, the interior of a thick lava flow can remain molten for months or even years, protected by a hardened crust that acts like a thermal blanket. Think of the island as a massive cooling battery of time, slowly and steadily releasing its ancient energy into the cool night air. Deep within the silence, there is a music to the mountain that our ears cannot always perceive, but our bodies can feel. Scientists use sensitive instruments called seismometers to detect harmonic tremors, low-frequency vibrations that typically occur between 1 and 5 hertz. These are not the sharp, jagged shocks of an earthquake, but a rhythmic, melodic pulsing caused by the steady movement of magma through underground conduits. It is the Earth's own heartbeat, a deep, resonant hum that vibrates through the basalt at a velocity of nearly 6 kilometers per second. And this sound is a constant reminder of the fluid energy that supports the solid ground, a steady pulse that encourages a deep sense of security and rhythm. At this very moment, you might imagine the more delicate creations of the volcano, born from the wind and the fire. When bits of molten lava are flung into the air and caught by high winds, they can be stretched into thin golden brown threads of glass, known as Pele's hair. These strands are remarkably fine, often less than 0.5 millimeters in diameter, and can be over 2 meters long. Alongside them, you might find Pele's tears, small aerodynamically shaped droplets of black glass that solidified in midair. Picture these fragile glass ornaments scattered across the dark basalt like jewels, a testament to the way the Earth can turn raw power into something of exquisite, a shimmering delicacy. Notice how the air around the volcanic vents, or fumaroles, carries its own unique chemistry. These vents can reach temperatures exceeding the boiling point of water, and the gases they emit are primarily composed of water vapor, about 90%, followed by carbon dioxide and sulfur dioxide. As these gases hit the cooler air, a process called sublimation occurs, where the gas turns directly into a solid. This creates crusts of native sulfur, which manifest as brilliant, neon yellow crystals. The scent is faint and earthy, a primordial aroma that has existed since the first rocks formed on this planet 4.5 billion years ago. These yellow crystals are soft to the touch, and they represent the Earth's internal breath being captured and crystallized into a tangible form. Scientists discovered that the cooling process also creates a visual rhythm in the minerals themselves. If you were to look at a slice of basalt under a microscope, you would see a beautiful mosaic of lath-shaped crystals called plagioclase feldspar, interspersed with the rounded green grains of olivine, or MgFe2SiO4. These minerals crystallize at different temperatures, a sequence known as Bowen's reaction series. Olivine is often the first to solidify, forming at temperatures around 1,200 degrees Celsius. This sequence of cooling is as predictable and orderly as the phases of the moon, ensuring that every piece of volcanic rock follows a strict mathematical harmony as it transitions from liquid to solid. Picture the way the ocean interacts with the island's edge. As waves strike the basalt cliffs, they dissipate an immense amount of energy. Roughly 90% of a wave's power is absorbed in the first few meters of contact. This constant rhythmic pounding creates hydraulic cooling, where the sea spray rapidly lowers the temperature of the coastal rocks. The interaction of the hot rock and cold water creates a white plume, known as laze. This plume is not just steam. It contains fine particles of volcanic glass and a small amount of hydrochloric acid, or HCl. While it sounds intense, from a distance, it appears as a soft white mist, a gentle veil that the island draws over its interface with the sea. What's happening now is a gradual settling of the entire island mass. This is not just a descent, but a slow-motion immersion. As the island moves away from the hotspot, the lithosphere beneath it begins to cool. Cold rock is denser than hot rock, and as it contracts, it naturally sits lower in the mantle. This thermal subsidence happens at a rate of approximately 0.02 millimeters per year. Over millions of years, this adds up to kilometers of movement. The island is essentially returning to the embrace of the Earth, a long, slow exhale that lasts for eons. It is a process that requires no effort, only the patient surrender to the laws of thermodynamics. Consider the sensory experience of the volcanic smog, or VOG. This occurs when sulfur dioxide reacts with oxygen, moisture, and sunlight to create an aerosol of fine acidic particles. These particles are incredibly small, ranging from 0.1 to 1 micrometer in size. They scatter the light of the setting sun, creating deep, saturated hues of violet and orange in the sky, a phenomenon caused by scattering. The atmosphere itself becomes a canvas, painted by the chemical exhales of the mountain, turning the evening into a masterpiece of refracted light and color. Deep within the structure of the island, there is a fascinating relationship between pressure and sound. In the deep basaltic aquifers, water moves through the pores of the rock at a very slow pace, filtered by the natural magnetism and mineral content of the stone. The sound of this water, hidden, secret, and pure, is a muffled trickle that resonates through the density of the basalt. Because the rock is so solid, it conducts sound waves with incredible efficiency. A small stone falling in a lava tube kilometers away might be felt as a tiny crisp vibration beneath your feet. It is a world where everything is connected by the physical medium of the stone. At this very moment, imagine the way the moonlight reflects off the different textures of the lava. The smooth, ropey pahoho has a high specular reflection, meaning it shines like a dark mirror. The jagged, fragmented Aa has a diffuse reflection, scattering the light in many directions and appearing as a soft, matte charcoal. This play of light and shadow creates a landscape of infinite variety, despite being made of a single type of rock. It is a reminder that beauty often arises from the simplest of materials, shaped by the most fundamental of forces. Notice the feeling of weightlessness that comes with understanding these vast scales. The island is not a heavy burden on the Earth. It is a buoyant expression of its internal heat. The gravity that holds the island to the seafloor is the same gravity that keeps the atmosphere wrapped around our planet like a protective shawl. You are a part of this gravitational embrace. As the heat of the day continues to radiate away from the basalt, feel that same release of tension within your own frame. The mountain doesn't hold on to its heat, and you don't need to hold on to the thoughts of the day. Scientists discovered that even the oldest seamounts, those that have been submerged for 60 million years, still retain their volcanic shape. They become silent cathedrals of stone on the abyssal plain, 4,000 meters below the surface. In that deep, high-pressure environment, the rock is preserved, unaffected by the wind and rain that wear down mountains on land. There is a permanence to this creation that is deeply comforting. Once an island is made, its essence remains, whether it is bathed in the sunlight of the surface or the eternal dark of the deep. The island is a master of patience. It waits for the plume to rise. It waits for the lava to cool, and it waits for the sea to reclaim it. It follows the rhythm of the Earth's rotation and the slow, steady creep of the tectonic plates. There is a profound wisdom in this lack of urgency. As you prepare for the final stage of your journey, let the cooling basalt and the golden threads of Pele's hair be your guide. The world is cooling. The tremors are rhythmic and soft, and the stars are steady in the dark sky. Every mineral is in its place. Every magnetic crystal is aligned. And you are perfectly positioned to transition from the world of the mountain to the world of the dream. As our observation of the volcanic island draws to a gentle close, we watch the final slow-motion steps of its majestic life cycle. The mountain has moved far from the mantle plume now, and the fires that once fueled its growth have gone quiet. At this very moment, a process of inevitable, graceful descent begins. The island is no longer being built. It is being reclaimed. Consider the step-by-step transition from a soaring peak to a silent seamount. First, the island begins to sink due to its own massive weight, a process called lithospheric loading, because the basaltic rock has a density of approximately 3.0 grams per cubic centimeter. It presses down on the flexible crust. As the crust sags, the island subsides at a rate of about 0.02 millimeters per year. Next, the forces of erosion begin their rhythmic work. The trade winds and the heavy tropical rains, which can exceed 10,000 millimeters per year on peaks like Mount Waialaeal, carve deep, serrated valleys into the stone. Simultaneously, the waves at the shore act as a horizontal saw, cutting a platform into the basalt. While this occurs, the biology of the sea offers a protective embrace. Around the sinking island, coral reefs grow upward to stay within the sunlit epipelagic zone, which extends to about 200 meters deep. In places like the Eniwetok Atoll, scientists have drilled through more than 1,400 meters of solid coral limestone before reaching the volcanic basalt beneath. This tells a story of a mountain that has been descending for millions of years, while life has tirelessly built upward to keep the summit in the light. Eventually, the volcanic peak disappears entirely beneath the waves, leaving behind a ring of coral, an atoll. But the journey does not end there. As the Pacific Plate continues its relentless slide toward the northwest at a velocity of approximately 7 to 10 centimeters per year, the atoll eventually moves into cooler waters, where the coral can no longer thrive. The island then becomes a guillot, a flat-topped seamount submerged in the dark, cold depths. Imagine the Meiji Seamount. the oldest member of the Hawaiian emperor chain. It has been traveling for 82 million years and now sits thousands of meters below the surface, nearing the end of its long migration across the ocean floor. At this very moment, the Guyot approaches the Aleutian Trench, a subduction zone where the Pacific plate is being pulled back down into the Earth's mantle. Here, the ocean floor is approximately 7 kilometers thick, and it is being swallowed at a rate that matches the steady, slow movement of your own fingernail growth. The rock will eventually reach depths where temperatures exceed 1,000 degrees Celsius, melting and becoming part of the mantle's slow convection currents once again. This is the ultimate recycling of the Earth, a planetary-scale system of metabolic quieting, where the old is dissolved to make way for the new. As the physical island returns to the deep, notice how your own body is settling into a state of profound, natural equilibrium. Scientists discovered that the Earth's gravity, which pulls at 9.8 meters per second squared, is what anchors these mountains and what now anchors your limbs to the mattress. You are part of this gravitational tapestry. Consider the composition of your own being. You are made of the same elements that forged the islands. The iron in your blood, which allows your hemoglobin to carry oxygen, was forged in the heart of a dying star during a supernova billions of years ago. This is the same iron that constitutes approximately 85% of the Earth's core and gives the basalt its dark, heavy strength. The oxygen that makes up 65% of your body's mass is the same oxygen that combined with silicon to form the volcanic crystals of the island. You are not merely a visitor on this planet. You are a localized expression of its chemistry. At this very moment, the hydrogen in the water that makes up the majority of your cells is an element that has existed since the very beginning of the universe, nearly 13.8 billion years ago. It is the same hydrogen that powers the sun, which is composed of roughly 73% hydrogen and 25% helium. Everything you are is a piece of the cosmic story, resting for a brief moment in this quiet room. As the narrative of the island fades, feel the internal warmth of your own body, a gentle mimicry of the Earth's core. The radioactive decay of isotopes like uranium-238, which has a half-life of 4.47 billion years, provides the heat that keeps the Earth's mantle moving. In a similar way, your own metabolic processes are slowing down, shifting from the high energy of the day to the low, steady maintenance of sleep. Your heart rate is slowing, your breath is lengthening, and the electrical activity in your brain is transitioning from the rapid beta waves of wakefulness to the slow, rhythmic delta waves of deep rest. Picture the comforting void of the deep Pacific, where the pressure is immense, but the silence is absolute. In the Challenger Deep, the lowest point of the Mariana Trench at 10,935 meters, the water temperature is a constant 1 to 4 degrees Celsius. It is a place of total stillness, a sanctuary far removed from the winds and the light of the surface. Let your mind descend into that same velvet stillness. There is no more work to be done. The tectonic plates will continue their slide. The mantle will continue its slow convection at a rate of 20 millimeters per year, and the stars will continue to emit their light, which travels toward us at 300,000 kilometers per second. Here the universe is functioning with perfect clockwork precision, and you are permitted to let go of the controls. You are a part of the stardust, a child of the volcanoes and the sea. As the heat of the day radiates away, leaving only the cool, dark potential of the night, repeat these affirmations of rest to yourself, letting each one settle like a grain of coral sand on the seafloor. I am as grounded and stable as the ancient basalt. My breath is as rhythmic as the rising and falling of the tides. I am composed of the same light and iron as the stars. I surrender my weight to the gentle pull of the Earth's gravity. The slow pace of the tectonic plates is the pace of my own rest. I am safe in the vast, silent beauty of the cosmos. My mind is becoming as clear and still as the deep abyss. I am a part of the Earth's eternal cycle of renewal. I release the day as the island releases its heat to the sea. I am drifting into the comforting embrace of the silent void. The islands are resting now, submerged in the indigo dark of the North Pacific. The volcanoes have spoken, and now they are silent. The stars above Hawaii are steady, and the deep-sea currents are moving with a quiet, icy grace. You are floating in this vast, peaceful ocean of sleep, where time has no meaning, and the weight of the world has been lifted. You are made of stars, you are built of mountains, and you are returning to the quiet source of all things. The journey is complete. The island has found its peace on the abyssal plain, and you have found your peace in the warmth of your bed. The earth is turning, the universe is expanding, and you are exactly where you belong. Good night.